It's a whiskey glass like that, but it's got the octocat.
Yeah.
Just gets the logo thing.
Okay,
great. Good afternoon, everybody. My name is Robbie King. I am engineer in the Data Plane Technologies group at Cisco. I've been with Cisco almost 19 years, 15 of which has been doing network processor programming, little board design here. And my slides are mostly text. I'm not I write code every day, don't create a lot of PowerPoints, so they're not quite as nifty. So, okay. So really what we're going to go through is a little bit about our the code base that is our data plane, done with it, and then how we came to be in ODP, the work we've done with the crypto, and the work that we're currently doing with our data plane and ODP, and then just a slide basically saying where we'd like to see things go. So our data plane, the code base, is about 10 years old, I think. Is that right, Blake? Roughly, yeah. It was developed for a series of ASICs that we designed in-house that are anywhere from 160 to 1,000 threads. And there is a lot of code. I mean, there is just a ton of code that has evolved over that 10 years. I know someone has probably done some metrics recently, but it's quite a bit. We have ASICs that are in development today that are going to continue to use this, and those ASICs have a lot of hardware assist in them. Some of the major ones are the new work distribution, mechanisms to keep packets in order, things to do work on packets in order and also atomically. And then we also have classification. We have several others, but these are the ones that are most pertinent to the ODP discussion. We have only, in the last generation or so, brought crypto onto the device. In the past, we've actually had crypto being done off-chip through a packet interface. Literally, throw the packet to the crypto device, he sends it back. And it's evolved quite a bit over the last 10 years. So today we have this same code base actually running on x86s. We have it on MIPS, PowerPCs, ARMs, as well as the cores that are custom cores that are in our ASICs. We have it bare metal in our ASIC. We actually have it bare metal on MIPS cores. We have it running as native Linux processes, and we also have it as in a virtualized environment. So it has mutated a lot of different ways. And we've also started to be able to leverage different crypto devices. In addition to the sending it off chip and bringing it back, we now have things like the quick assist model where you do all these things in parallel, basically, and that's capable of OpenSSL, things like that as well. So, there's been a lot of changes to that code base to try to incorporate these different models of hardware assist, specifically crypto. So the first time we put it on to merchant silicon, we investigated a lot of different things. We decided that we would run it bare metal, so there's no operating system. There's just basically a very simple executive that, for the most part, we don't make too much use of. The device was a good fit as far as what our ASICs do and what it does, so that it was easy to envision how you could incorporate it into our code base. It has support for work distribution, packet ordering, ordered atomic code sections. It has some support for hierarchical queuing and scheduling. Our ASICs do a lot of hierarchical queuing and scheduling on the device and hardware. But this was a good fit as far as being able to give a base implementation to build a software version of that on. And then it does crypto. one of the big problems with this was, you ended up, even if you didn't really want to, we had a variety of reasons for doing it anyway, but it's sort of hard to run bare metal on some cores and actually run Linux on the other cores, to try to get that all partitioned out so that Linux doesn't want to take control of other things and leaves everything alone and interrupts and all that stuff. It was a lot easier just to say, look, this guy is going to run bare metal. This chip over here is the control processor. It runs Linux. And it's a nice split. And while it does do these hardware assists very well, there was a huge amount of work to actually pull that into our code base and integrate it. Most of that was done from scratch. Some SDK code was leveraged, but a lot of it was done, from the CSRs up. The other thing is that we had to sort of reinvent the wheel when it came to infrastructure. On our ASICs, I actually owned the code that generated core files. So if one core in the ASIC crashed, we generate a core file that is ELF format. You can somewhat access it with regular GNU tools. On this bare metal device, we had to do all that again, and that was one example of just the work that went into accounting for the fact that we didn't have an operating system really. So as we went forward, we said, wow, that was painful. Can we do this in a maybe not quite as performance efficient way, but with much less overhead from a development standpoint? So we have then since put all this into running as a Linux process. So that fixes some of those problems. We can run the control plane and the data plane on the same device. If you can get Linux up and booted on a device, we can get going pretty quickly with it. And then you have all that wonderful infrastructure for, you have disk support, you can create core files when something crashes, you get all that sort of for free. One of the downsides is you are still, even if you very carefully, isolate your threads into cores, you structure your code so you really try to stay out of anything that's going to go into the kernel. You still have some of that. You're going to get interrupted on the timer tick no matter what, unless you know Hertz or something like that. But we, have to be very diligent about watching out for, you can't let something sneak in there because it will really trash your performance. And keeping things pinned sometimes is hard, and steering interrupts. And hardware assists are very difficult. If they're in the kernel, then there's that whole how do you efficiently get in and out to take advantage of it, or how is your code structured to make sure you're getting the advantage of it. And user space, if and when you can do it, then you have the problem of each vendor's SDK is going to be, people like to draw their APIs at different levels. Sometimes they accelerate things in a different fashion, so you still got a lot of work, even if you're going to leverage that vendor's SDK. You've got a lot of effort and engineering manpower just to adapt your code to it. So there was an initiative internally. We have all this code that runs on the ASIC, and we have we had internally said, okay, this is the layer where it's the hardware abstraction for a given piece of hardware assist. And there was an effort to say, well, could we take this and somehow standardize it, at least for something we could give to vendors and say, hey, if you're going to accelerate this particular thing, we want you to do it this way. Turns out that the way we did it in our chip doesn't really fit nicely to the way most anybody else did it. And it's sort of hard even between them to envision how you would do that. So it was determined that, wow, this is going to be a hard nut to crack, and we'll talk about how crypto fell into that here later, or here in just a second. So, we really would like to be able to use merchant silicon. The group that we own, or that Blake owns responsibility for, we are now doing products down to pretty small. So, things that don't make sense for us to do an ASIC for.
10 megabits to 400 gigs.
Yeah, 10 megabits to 400 gigs. So that's a pretty hard thing. You can't go off and create our own. We can't go off and make our own chips to cover that whole spectrum. So, if we can use off-the-shelf stuff, that's great. And if we use something off the shelf that our competitors are using off the shelf and they're driving the price down, that's even better. Problems that we have is that a lot of vendors sitting in this room have devices that are really cool and have all kinds of great hardware assist that make the dollar per flip-flop cost of this chip attractive if you can exploit it. The problem we have is there's for the variety of reasons we've talked about, it's hard for us to do. And so a lot of times it's a great device. It would be a great fit if we could use that hardware assist, but we can't. And so you can't really do an apples-to-apples comparison of just the raw throughput of the device, its power consumption, how much it costs. It makes that very hard to do. So looking at OpenDataPlane, that looks like a great opportunity to have a set of APIs that the vendors can go to, and it's a high enough level of abstraction such that we can fit that into our code, and now we get to take advantage of all of these different vendors. That's a great thing for us. It's going to be a great thing for the community in general, because it means you can develop one open source app, and you can quickly go from device to device. It's really good for everybody. And for us, honestly, we want to open up as many vendors as possible so that we get the best bang for the buck when we put a device on a embedded product. So, as I was saying earlier, the whole spectrum of APIs that we could tackle. There are things that are harder and things that are easier. One of the things that had been very challenging for us, and we had ended up putting a lot of engineering effort into, is moving from one crypto device to the other. And so we decided that would be a great thing if we could at least have a common API to code to for crypto. Cisco actually internally, probably beginning maybe a year and a half, 2 years ago, began creating their API definition called SDAL, which is this device abstraction layer, and tried to start simple with just something that's basically for symmetric key operations, and the APIs are designed to work synchronously and asynchronously, both for session creation and per packet operations. And we have vendors who have taken that specification and coded to it. And so while that work was going on, it was still going to be sort of a one-off kind of thing, whereas making this more a part of, say, OpenDataPlane gets to be more of a ecosystem to develop in, because I know as we've worked on crypto for the last 6 months, and I've looked at how it would integrate into our code, we very much took the approach that we'd like it to be a la carte, that you could pull in ODP and its crypto implementation and leverage it without having to pull in all of ODP, but at the same time, you have to be able to do it efficiently, and that's it's a balancing act. So we, I guess at LCA, the steering committee, Cisco said, hey, it'd be really cool if we could get a crypto API to be part of ODP, and everyone agreed. So we've been focusing on that. One of the things we've been focusing on for the last 6 months.
I think one of the other points there, Robbie, is that the crypto was one of the things that the majority of the vendors had in common. Like you said, each vendor has their own specific secret sauce, et cetera. Certainly everybody does crypto differently, but the vast majority of vendors and participants also felt like that had a lot of value, I think.
Yeah, that's a good point. And so what we, from our standpoint, we hoped that what was envisioned by ODP would also give us at least the similar level of functionality as what we had targeted with SDAL. not necessarily how you accomplish, as long as you accomplish the same end result that you encrypt and decrypt synchronously and asynchronously, the nuts and bolts of it, we wanted to leave that to be very much, ODP, not to try to enforce too many artifacts from our API into ODP, but we did want to be able to say, hey, can we do this as a little subsystem and integrate it into our system as a whole? So the deliverables were that we would have a good detailed API specification, a reference implementation in Linux generic that was just, not performance optimized, but was something that you could say, if my code behaves the same way as that code, that's the litmus test. That's not to say that we don't need conformance tests as well, and that's something we've talked about in the other meetings, but that was the idea there. And then we also have an example application that was really intended to exercise the API, not even so much in a performance method, but just to ask all the aspects of it, the synchronous and asynchronous nature, in the various buffer modes, which we'll talk about just a little bit. And then we also said that, hey, wouldn't it be great if we had some test application that could actually really exercise the API on the various hardware implementations and see what kind of performance, if there are performance issues, do some metrics. And then the real stretch goal was the Cisco Data Plane making use of it. So as far as where it's at today, I believe revision 1.0, or maybe even 1.1 is in there, the spec. The reference implementation is in the main repository. It's been there for about a month. It only does triple DES, MD596 for cipher and authentication. Does that using the OpenSSL crypto libraries. So, performance-wise, that's whatever you get from those, that's what you're going to get with Linux generic. It does do sync and async versions of the session creation and per packet operations. And it also emulates the various buffer modes that are defined by the API, which is you can have your crypto operation occur in place in the same buffer. You can have it copied to a new buffer that the application provides, or you can have it go into a new buffer that the implementation provides. And so the idea there is to try to support the actual workings of the different implementations that we had to reference. We do still have a couple of open items. One of the things that has been a big thing for me is to make sure that we have the right methodology for efficiently keeping packets in order. For us, if it comes into box in an order, it has to go back out in the same order. That's just sort of a fundamental. So being able to do that in an efficient manner and do things like assign sequence numbers, some hardware can do the sequence numbers itself, some can't. So you need to be able to have a way forward to get there with high performance. And then one of the things that SODAL specifies that we've not gotten to yet with the crypto API is a way for the application to query the capabilities and capacities of the particular implementation, so that if it needs to adjust for the fact that some particular cipher isn't supported, that we need a way to find that out at runtime and account for it. So from the applications, the example application, I think the patches went in last week, and we're going to be demoing several different vendors of that here next day or two. And it was really to verify that the API was usable to accomplish, a detailed piece of work. So, it actually goes through and has to do the work of creating an IPsec packet with the ESP and AAH header, and gets to really flip all the bits of the implementation of the API. The performance test, Victor has been working on, has done a great job with it, and has it running. I think you still got, actually you sent your patches, didn't you? So, yeah, and so that's been very nice, and we have some results on the next slide. And then from the data plane, the crypto API, part of that's, oh, I'm sorry.
Does the IPsec example do the ASIC creation itself?
No, this is all just cipher and authenticating. That's it. Yeah. Cisco's the full CIDAL API that they have specified has a lot more and has those kind of capabilities specified as part of it. But even for the work we've asked the outside vendors to do, we still kept it to this basic functionality. And the ODP API will also, surely evolve to include those kind of things. But for today, that's not included. And I think actually someone even sent a patch very recently, starting us down the path of thinking about how we will get there. As far as getting it to work with our data plane, part of that's been gated by me getting our data plane just functioning on ODP. Now, granted, we made the statement that we didn't want to require that to happen, but it started to make more sense since we're going to do that work anyway. Let's see it work that way. One of the biggest problems we've had is the work I've been doing with our data plane on ODP is in what we call a headless environment. So the control plane's not actually there. It's statically configured when you boot it up, and it runs all by itself. And the crypto group has never done the work to actually support statically configuring IPsec. So that's probably the bigger work item than integrating ODP into it. So, but I mean, we have that scheduled. It's just, a matter of priority and when it's going to happen. So, just a little bit about the example app is, it's nothing very fancy. It works very similar to setkey as far as creating your security associations and stuff. Forwards packets, you can actually disable all that, and it will just IPv4 route packets between two interfaces based on static routes. It only supports transport mode, which was a undersight, or an oversight, I should say. Tunnel mode would be a lot easier to do testing in the lab with, because then you could terminate the tunnels with a router. So that's a bug that we recently created to get that in there, because it would make some of this analysis going down the road much easier to do. And it has live traffic, which is what we will be demoing, and it also has a sort of a standalone mode where you can feed it test packets, let it run through the crypto implementation, verify what comes out the other side, using the OpenSSL libraries to allow you to quickly do a standalone test of a piece of hardware, of our hardware implementation, without having to have all the traffic set up in it. And it does make use of a lot of the fundamental constructs of ODP as far as it runs multi-core. It will call either ODP schedule or use hold queues, makes use of ordered and atomic queues. So it exercises quite a bit of the buffer management and all those pieces that you need to build a system. The test app that Victor has done, he has it running on the TI Keystone II. Did some comparison work against the Linux generic implementation versus the Keystone. And it pretty much starts a loop, really hammers on it, issuing as many requests as it can, sees how long it takes. The points that were really needed to be pointed out was that neither one has really been optimized for performance yet. The Linux generic may never be, and I know Taurus is, that's one of the things that he wants to get to, but it's, it will take time. But even with that, it's pretty impressive that the difference between the Linux generic and the Keystone is about 22 times. So, that API is doing pretty well as far as letting us access that. Now, I'm sure as we refine the Keystone implementation and do a little bit more a little deeper in-depth digging at it, there are probably plenty of bottlenecks and things to uncover and fix, but it was nice to see that it didn't go slower.
Which is often the case first.
Usually is the case, yeah. So this is just a quick thing of the vendors are going to be demoing this week, and this was just a list of them along with the modes that the per packet API operates in. So this is about our data plane on ODP, which is what I've been focusing on for the last few weeks. You know, the crypto API, that's something that's, to Blake's point, that a lot of our vendors have crypto. This is, it's a good cross-section, something you can leverage. What we've found as we've looked at more and more at, if you have a 4-core device, hardware assist for packet ordering and work distribution, the fewer the cores, the less likely it is that a hardware assist is going to buy you a lot as far as core-over-core scaling, because you're probably going to dedicate one of those cores to your control plane, one to run in your packet processing, and so it's not as much bang for the buck. But if you start getting into something that's got 16 or 32 cores, tricks like pinning flows to cores and things aren't really as useful. And so having hardware assist that can efficiently let you do work on one flow in parallel on multiple cores becomes more and more important. And so the idea with putting our data plane on there is to give us a way to see, for a fairly sizable multi-core device, is ODP going to give us a mechanism by which we can efficiently leverage hardware assist on these devices and do that work once and then be able to reap the benefits of it. The key things that we make use of is we use ODP schedule. That's really the fundamental basis of the work distribution. Packet ordering using the ordered and atomic queues. The buffer management sort of goes without saying, and crypto will be a part of that at some point. And so I have just a very rough picture here of how it's currently architected. As a packet comes in off of the wire, goes through the packet I/O input queue, gets dispensed out of the scheduler. Our code is going to take that work coming out of the scheduler, do what it can. If, for instance, we wanted to say assign a sequence number that would need it to be in the order of the flow, then we're going to send that packet back through an atomic queue, back through the scheduler, and then expect to be able to work on those packets in order one at a time when they come back through the scheduler, before finally sending it back out the packet I/O output interface queue, and goes on its way. And of course, the buffer manager is helping us in the background, eliminating all that overhead. Excuse me. And the ordered queues, there it's more a statement of, if you want to try to, especially say if you were going to do some atomic sequence number processing, if you have multiple flows that need that kind of work, you would like them to stay out of each other's way. And so the idea with the ordered queues is to be able to put different flow IDs into different ordered queues such that you can try to eliminate as much headline blocking as possible. We have found that there's a sweet spot there. Sometimes you can actually do more work trying to get flows out of each other's way than if you had just let them headline block and didn't go through all the overhead. And so where I'm at with that currently is I have it forwarding v4 traffic on x86 and ARM with Linux generic. Been working with Taurus this week, trying to get the Linux Keystone set up to be able to integrate with that as well. And we'll have a demo of ping traffic going through it tomorrow. As far as where we'd like to go next is, as more ODP implementations have the infrastructure and can give us the SDK and an ODP drop, we'd like to start targeting those and then really start getting into getting the kinks out of it and understanding the performance, whether bottlenecks, things that could be improved. Hopefully leading up to being able to do things like how does it behave when it's oversubscribed? How can we treat priority traffic? With an eye to how well does it integrate with our code, but also how well do the ODP APIs today, do we have the knobs there that allow us to really do this effectively? And then, of course, try to get the crypto in there at some point. And in summary, one of the big things this week is to try to figure out what needs to be done for ODP 1, and then going beyond that for 2.0. And I think really from our standpoint for ODP, for the 1.0 release, is really to try to finalize the rest of the APIs, sort of fill out the slate there, and get them in place. Then it's okay if they're not perfect. That I think the goal has been stated that 1.0 should be for really about evaluation. So if there's something missing here and there, or there's the pointer's not a const or something like that, it's okay. And one of the other things that would be very nice is to have is for each of the API groups is compliance tests, to be able to say, at least be able to go from implementation to implementation and see that they are behaving the same across the board. And really beyond that, from our standpoint, it would be really nice to be able to, sort of to the previous slide, looking at performance and the system behavior from QoS standpoint, things like that, is getting the APIs, the details worked out, the missing pieces that need to go in, whether it's missing functionality or missing control, missing feedback information. We had some good discussions yesterday about queue depths, all kinds of things like that that might be part of that. But getting to the point that 2.0 is something that you could say, I could build a viable product with, that might not be where you ultimately want to go performance-wise, but that you see a clear path. And I think that's pretty much it. So if anybody has questions, yes?
Sort of a technical question, but I'm just curious. It's about the use of the atomic kind of queues. Just to understand, so suppose some hardware or there was some mechanism to magically assign IPsec sequence numbers and check them even in parallel. Would you still require or need atomic queues? I mean,
yes. Yeah, multi-link PPP. I need to put sequence numbers on packets in order.
Again, just assuming there's a magical way to resolve sequence number and sequence number validation. I'm just trying to figure out if the use cases is just this kind of sequence number validation, if some magic resolve that. Is there any other use case that just...
No, I think, one of the things that makes our code base so important to us is the stateful features that we do. There are a lot of somewhat, you can call something like MLPPP, it is a stateful feature, but the amount of state that's really important to make it that is pretty small, like a sequence number. But we have features, firewall, NAT, trying to think of some other good examples there where, there's actually a lot of, if we go into an atomic code section that we want, for this packet to stay, single file through here and in order, we're going to do a lot of disjointed work there, updating data structures, things like that. And so, an atomic, the construct of an atomic code section, if there is a way beyond atomic queue to accomplish it efficiently, I think that would be good. But right now, what is defined for ODP, I think that's what we have to be able to accomplish that kind of work.
Okay, and I guess it's okay for you if, I'm just thinking if you have like a, large multi-core and if you have many flows, okay, no problem. Large multi-core, single flow, kind of can't use it, but I guess, you're not bothered with that, right?
Yeah, we understand fully that the price of having a common API like this means that we will perform worse on everything as opposed to if we custom coded to each device. I don't want to say least common denominator, but at the same time, there is some of that, right? You know, but for us, the difference between that and not leveraging hardware assist at all is, you know, if ODP can give us a really good performance boost, you know, that's certainly better than not doing it all. And development resources may be the thing more than anything that dictates. You know, we just can't. We don't have the manpower to go target 10 vendors' devices and tweak it to that point.
It's an ROI statement.
Right. Now, you know, if we said, you know, look, it looks really good on this device, and this is, you know, for this, you know, we're wanting a product that has this price point, this throughput, these interfaces, and this device fits the bill. And then we said, wow, the crypto performance, yeah, you know, I'm sure that's the point where we go, wow, we put 2 guys on this, they work on it for 6 weeks, and we can leverage this piece of hardware assist, and it's doable either through some new construct of an ODP API or perhaps through the vendor's SDK. You know, we'll make that trade-off. But, you know, in general, you know, the idea is to have a consistent basic level of functionality that's available across these devices that gets us, you know, work distribution, packet ordering support, buffer management, and I/O. Yeah.
Okay, thank you very much.
Mm-hmm.
So, one of the features of a product I'm working on has metering support with hardware assist. I guess the question both for you and for the community, if there's been any effort in metering, extend the APIs for that.
So when you say metering, is that like policing?
Policing, ingress,
Yeah,
ingress
okay.
policing, determine a color, marking, DP.
Right. I mean, that is a hardware assist that we utilize. I mean, I don't believe that it's really come up yet as one of the APIs that are under consideration today. You know, I think one of the big things that sort of drives which APIs to tackle first is the cross-section of vendors. You know, if you have 8 hardware vendors participating and one of them can do policing acceleration, let's save that one for a little later. If 7 of them can do hardware acceleration for policing, let's talk about that one. Yeah, that's you know, the more bang for the buck early is probably the best way to go. But yeah, I agree with you. That is something that, you know, hardware assist for is nice. Okay.
Maybe in this context, it makes sense. Maybe in the context of what you're saying and servicing what you're trying to achieve, would it make sense that all participating hardware vendor will make just a shopping list of, you know, one line item so it won't be confidential? We can provide hardware assist for this, just so we, you know, the obvious will come up.
Yeah, I mean, I think that would be great. You know, one of the things that we've, you know, talked about informally internally is a person who was participating in the ODP project that really had the task of going off and understanding each vendor's devices sort of to a next level of functionality. So because that one person, and unfortunately that has to be sort of a neutral person,
Yeah.
has to, you know, could go off and really start to put together this picture of, you know, these are the similarities between all these devices, and here are the places that they're really disparate. And so, you know, I mean, myself, I'd love to be able to go do that, because then that would help me envision, you know, how if it's feasible, there's a path to taking our data plane and mapping it onto this family of devices, and I see a clear path to all of them through a common API. Make me feel, you know, that would give me much better warm and fuzzy feeling about, you know, if we can make it work.
Sounds like a good idea, and it sounds like something which is perfect for Linaro, right? Because of, you know, the neutral kind of thing.
Yeah. Unfortunately, I have to make him happy. That's job one. Well, it is 2 minutes till to lunch. So if nobody has anything else, thank you. Appreciate your time. All right. So if I do this, it'll give up. What's it?
That was a shameless plug.
Oh, yeah.